It's a very great pleasure to introduce our speaker, Dr. Erik Blaufuss, from the Physics Department of the University of Maryland. He's in the Particle Astrophysics group there. He earned a BS in Physics, Bachelor's in Physics from the University of California at Irvine, and a PhD in Physics at Louisiana State University in Baton Rouge, which is not far from where one of the His PhD thesis studied the energy spectrum of electron neutrinos from the sun, having energies above 5.5 MeV. And for that, he used data from the Super Kamiokande neutrino detection array in Japan. At Super Kamiokande, he measured both the flux density of the neutrinos and designed and operated a portable calibration device that generated high-energy neutrons. And he also maintained a computerized system that monitored the quality of the data. Beginning with that thesis work, his research has really focused on measurements with high-energy neutrinos. After his PhD, Erik joined the University of Maryland's Particle Astrophysics group, where he works on the IceCube Neutrino Observatory at the South Pole, which he's going to tell us about. And he had also been working simultaneously on the Milagro Gamma Ray and Cosmic Ray Observatory in the mountains near Los Alamos, New Mexico. Milagro worked by using the light produced by the Cherenkov effect, by the large shower of fast-moving charged secondary particles produced when an incoming gamma ray or cosmic ray hits the atmosphere. Milagro has since been replaced by the University of Maryland's high-altitude water Cherenkov Observatory on the flank of a volcano in Mexico. Dr. Blaufuss.
Thanks. So it might be better, some of these things are going to come out, be washed out if we can get some of the lights up here turned down. So it's my pleasure to be here today and to tell you about IceCube and how it works.
That
works. That looks great. And I would encourage everyone, especially with the size of the group, to if something is bugging you, you have a question, please just interrupt me and we can answer questions on the fly, or you can hold it till the end. It's up to you. This is a picture of IceCube. It's about all you can see right now. Most of it is not visible. It's well below the surface of the snow. But this building right here is the counting house where all the wires from all the detectors come. It's a two-story building, and the wires come up this thing and into the thing. These are great photographs that we get from our winter rovers that live and work at the South Pole and watch after IceCube and keep it operating all the time, 24/7. And this was a picture, and you can see a nice view of the galactic center rising over the detector. So it was a really nice picture. You heard a little bit about me already. I think that I'm a research scientist at the University of Maryland. I've been here for almost 20 years now. My entire career has been doing neutrinos and particle astrophysics. I am not really a great astronomer. I actually consider myself a bad astronomer because the terminology, and I always have to stop and look it up, but I'm learning. I spent, as a graduate student, a lot of time in Japan working on Super K, and my current interest is mostly been on the IceCube experiment, where I kind of lead the real-time alert effort, where we send out real-time alerts to the community when we see interesting events. And I've also been keeping my eye on this deep underground neutrino experiment, which is being built at Fermilab. So since this tends to be more astronomy focused, and I'm not sure the background of the group, I figured I'd at least tell you what a neutrino is. Back in the 1930s, people were starting to study nuclear decays and those type of things, and they came across this beta decay, where an electron's being emitted by a radioactive decay. At the time, the theoreticians came along and said, well, if we're giving off this electron, it's all the energy from that nuclear transition should be coming out in that neutrino, and you would expect to be seeing all the electrons coming out with a single neutrino, a single energy, And that's not what was observed. They would see this continuous spectrum here. So Pauli postulated at the time that, okay, there's a third particle coming out which is taking the remainder of the energy. We'll call it a little neutral one, neutrino. And that's where this particle was born, and it's now a part of the standard model. And I think one of the things that bothered Pauli was that he predicted a particle that could never be detected. And actually, we do detect them, and we use them quite frequently now in several kinds of observations about studying the neutrino and now in astrophysics. So it is a key member of the standard model of particle physics. This is the model of how the universe works, how the subatomic universe works, that particle physicists use to describe everything you see happening at the Large Hadron Collider. And they spend all their time smashing these things together, looking for things to not agree with the standard model. And so far, it's agreed very, very well. Neutrinos are down here. There is 3 types, each one matching the 3 leptons. So everything you see in the normal universe is made up of this first generation here. So protons and neutrons are all made up of up and down quarks, and electrons make up the rest of the atom. That's making up the majority of the universe you interact with. Everything else out here is being created in these particle accelerators, and they're a lot rarer. It takes a lot of energy. They're much heavier in mass, and it takes a lot of energy to create them. But there are 3 generations of these leptons: the electron, a muon. You see a lot of muons in cosmic ray air showers reaching the Earth, and the tau particle is even more rare to see. But there are neutrinos that match each of those things. One part of the standard model we know is incorrect is the description of neutrinos. In the standard model, they're massless, but we know they have mass. And that leads to some interesting physics that go along with neutrinos. Since neutrinos have mass, and so every neutrino that is an electron-type neutrino is made up of different mass states. And when these things propagate in the vacuum, they propagate in one of these mass states at a fixed energy. And what that causes is it causes the. Yeah. I guess I'm boring somebody. The electron-type neutrino will change due to quantum mechanical effects. Neutrino oscillations are what they're called. Will change from one type to another. And that probability you can see here. So if something starts out here as one type of neutrino, this is an electron neutrino, and it propagates in some distance, it'll then slowly change from one type to another, and then slowly oscillate back. But this has, so we use these property to study the neutrino itself at places like Fermilab and CERN, where you create these beams of neutrinos, allow them to propagate, and measure them again at the second place, and you can understand the properties of the neutrino, how much each type of neutrino, and that's where we can build this model, is from those observations. What type of neutrino? We can use neutrinos from the sun as well to do these similar types of observations, to say that, okay, electron type neutrino is 2/3 type 1, 1/3, and a little bit of type 3. This is where we get all that information. But what it means for us in IceCube is neutrinos created very far away are fully oscillated. They're fully mixed up. So if it creates one type of neutrino, they get fully oscillated and they become, so a flux of neutrinos from a source is 1/3 electron type, 1/3 muon type, 1/3 tau type when it reaches our detector at Earth, because they have such a long distance to oscillate over.
If we don't get too involved here, what causes the minor little oscillations?
It's an interference between the different phases, right? So it's not just an oscillation between 2 types. It's three different flavors can oscillate, and they have different frequencies. So you're seeing different beatings and different amplitudes of that oscillation. And that's what gives you this kind of wiggle on the larger oscillation. So one of the main drivers, and I'll get to why neutrinos are connected, where we're trying to understand cosmic rays. We see the cosmic rays rain down on the atmosphere all the time from Earth. They were just, really identified as coming from outside the Earth 100 years ago by Victor Hess, who went up in this balloon to very, very high altitudes where he needed, had difficulty breathing. It's an amazing experiment when you read about what he did, going up in this experiment in the cold and running an electroscope and seeing the flux of cosmic rays being higher up in the atmosphere than it was. Instead of the assumption at the time that this radiation you're seeing on the surface of the Earth is coming from the Earth, and if you go high enough, it'll go away. So this established that these things are cosmic rays coming from the universe, hitting the Earth, and really started a 100-year thing, a 100-year search for where they're being created. Roughly 25 years later, Piaget, working in Switzerland, was able to observe particles, correlated particles from a single cosmic ray interacting high up in the atmosphere, and really led to this idea of what the cosmic ray is doing, especially the high energy ones, when they reach the Earth. These cosmic rays come in, strike some atom high up in the atmosphere, and they create this huge shower of particles. And that's what you observe here at the Earth. And what way he was able to establish this was seeing, two greatly separated detectors seeing particles arriving at the same time, repeatedly. He was able to postulate that these are coming from the same parent high up in the atmosphere. So here on Earth, this is what we live in. We're constantly bathed in this radiation from cosmic rays. Most of the interesting stuff is very short-lived and does not go very far into the atmosphere. But the ones you see striking the bottom of the Earth here are these muons. Muons are very stable particles. They don't lose energy very quickly. They have lifetimes that exceed several microseconds and will propagate from where they're created through and deep into the Earth, where they'll eventually stop. Additionally, you'll see that there are these neutrinos. We call these atmospheric neutrinos because they're created in the atmosphere by these interactions of these cosmic rays. And they represent both of these, the muons and the atmospheric neutrinos, represent a huge background for IceCube. They're the predominant things we detect at the South Pole, not the astrophysical neutrinos. And I'll give you some idea of what those numbers are. But people have been measuring the spectrum of cosmic rays now for, that kind of got cut off, sorry about that. So we've seen, if you look at the energy of these cosmic rays, they go to very, very high energies. We have no idea what is producing these cosmic rays out here at this energy. There's so much energy being produced in them. This is kind of the scale of the highest energy particle accelerators we can build here on the Earth. And then this is, 6-7 orders of magnitude higher in energy. And we have no idea how, we have ideas what the mechanism is, but we have no confirmation. We have no confirmation of what the source of these things are. These cosmic rays go out into space, get wound up into magnetic fields, and really don't point back to where they came from. But they're also very rare out here. Right, so it's a 100-year-old mystery. What is the source and location of that are accelerating these cosmic rays? What is its composition? What is it made of? Are they protons, or are they very heavy nuclei that are being accelerated? You can accelerate a heavy nuclei much more quickly because it has a much larger charge. So it takes, you get much more energy, but they also start coming apart at some. And then where are things transitioning? We have models. We think we understand the lowest energy cosmic rays. We think they're coming from the sun. Slightly higher cosmic rays, we have a pretty strong association with supernova and the shocks, but these highest energy ones, it's a mystery. And this kind of bending behavior kind of hints at some are extragalactic, some are galactic origins. And this is a transition region where things are no longer contained within the galaxy, and you see a different population coming in. So what's the connection with neutrinos? Any place out there where you have an accelerator, say at CERN, and you create these high energy protons and they hit a target, you create a lot of debris coming out of that interaction. But one of the things you do create are these kind of protons, electrons are charged, and you also create neutrinos in these basic interactions that you see of these protons with matter. And that's what we're really using neutrinos for, as an indicator of what are the sources of these cosmic rays, right? So you have these sources out there, be they black hole, merging neutron stars, gamma ray burst, whatever they might be. They're producing high energy electrons, high energy protons. These are going to be in dense environments, not just a bare source. They're going to interact with things around them, particles in a jet, particles in the medium or directly around them. Those protons will interact, create this beam of neutrinos of energies matching those cosmic rays. So we're looking for these very high energy neutrinos coming from these sources. Where the protons accelerator are going to go off, find magnetic fields, get spun up by magnetic fields, take long windy paths, and eventually reach our Earth uncorrelated with anything we might observe. But the neutrinos, down here I think the neutrino sign disappeared, and the gamma rays and photons will come directly to us. But why are neutrinos more interesting for these to identify these sources than gamma rays? Lots of things in these sources can produce gamma rays. Electronic processes can generate lots of gamma rays. And they're not a strong indication, and it takes very detailed spectral studies of the gamma rays to say, that looks like a source with electrons, that looks like a source with cosmic rays, hadrons, protons, and iron. Where neutrinos, if you see neutrinos from a source, it's cosmic, it's protons, it's those type of particles, not electrons. There's no cross-section, there's no ability for those things to make a sufficient number of neutrinos to be detected on the Earth. So we're using the neutrinos, as this kind of smoking gun. That's where the cosmic rays are, a potential source of cosmic rays, right over there. But neutrinos have other problems. They're very weakly interacting, so you need a very big detector. But there are lots of parts of the universe where, for some reason or another, photons aren't going to reach us, especially at the highest energy, where you're really seeing these very energetic sources. You know, at these highest energies out here, where only neutrinos are going to be able to reach our Earth. Everything else is going to be, the gamma rays are going to interact with other particles or other photon fields before they reach the Earth, and they're just going to be wiped out before they reach the Earth. But neutrinos, with the low cross-section, can go through matter, can make it through, cloudy environments and still reach us here. So we're using neutrinos as this cosmic messenger to really understand the high energy universe and find the sources of the highest energy cosmic rays. So again, another picture from the South Pole. I always feel bad focusing on this building, but all the great pictures that our Wind Rover sent have this building in it. It's a small part of the detector, but this is the aurora that you see at the South Pole. Our Wind Rovers are down there taking these photos and sending them back to us every day. It's an amazing place. So how do you detect these neutrinos? What we're looking for is a neutrino incoming and interacting with a neutron or a proton within one of the atoms that makes up the ice that is IceCube. We instrumented a large volume of ice. We use the natural protons and neutrons in that ice as our target. The neutrino will come in, undergo this interaction, and out will come these high energy electrons. They take away the energy that the neutrino had coming in. So if this is a very high energy neutrino, you have a very high energy electron or muon or tau particle going out of this interaction. And it basically breaks up this nucleus.
Excuse me, what's this W that keeps?
So this is a subatomic force carrier that is exchanged in this interaction. That kind of when you want to understand how you can do mathematics. This has a mass. It's a virtual particle that's exchanged between the neutrino, the outgoing particles, and exchanges that energy between the two.
Thank you.
Mm-hmm. So neutrinos are actually very difficult to detect. For example, if you hold out your thumb towards the sun, 65 million neutrinos per second pass through your thumbnail. Those are neutrinos from the fusion reactions that are happening inside the sun. They're lower energy than the ones we studied with IceCube, so they interact even lower. The interaction probability rises with energy. But this is kind of gives you an idea of how long. So your entire life, you'll be bombarded with trillions of these neutrinos, and I think in your lifetime, they say that maybe one will interact within your body during that time. And it's a low enough energy that, compared to the other sources of radiation you're exposed to, it's not a worry. So to detect this outgoing charged particle, we use something called shrink-off radiation. So shrink-off radiation is these relativistic leptons produce optical light in the ice. This is an effect of shrink-off radiation. It's when the charged particle is moving faster than the speed of light in the medium, it generates this blue light. Similar to what you see with a supersonic jet, a sonic boom. And these particles leave distinct tracks. As this muon or electron travels in our detector, giving off the shrink-off radiation, we see that light with our optical detectors, and we're able to reconstruct that pattern. This is what that shrink-off light might look like. This is a reactor where they're putting out a lot of energy into the particles, and you see that blue glow, and that's what we're detecting. So IceCube works something like this. Here we have the neutrino coming in, having some interaction. Doesn't necessarily have to be within IceCube for some of them. We create this muon. This muon then travels through IceCube, all the time emitting this light blue glow. We've sunk these sensors into the ice. They detect the time and the amplitude of the light from these things. We're able to then use that time and amplitude pattern to reconstruct this direction. And this direction then is tightly correlated to the direction of the neutrino at these energies. It's a very strong Lorentz boost. So it's very close moving. Everything's moving close to the speed of light, so it's always go in almost identically the same direction. The angular difference you see here is much less than a degree at these energies. To do this, you need a very large source of either water or ice. IceCube is not the only shrink-off telescope detecting neutrinos out there in the world. There's one in the Mediterranean, deep in the water. It's a little smaller than IceCube, but they're building their next generation, which is going to be a similar size to IceCube. But we went to the South Pole, where there is thousands of meters of very clear, deep, dark ice underneath the South Pole. The South Pole gives us lots of great infrastructure to work. People live and work there year-round. We get power, we get food, communications, everything the people who are down there need to be able to operate our detector at the South Pole. We are at the South Pole Station, and there's another one you may have heard of, McMurdo. That's the big base on the coast that everyone goes through on their way to the South Pole. And it's here at the Ross Ice Shelf. So this is the detector we built. We do call it IceCube. It's not technically cubic. It's hexagonal in this dimension and then somewhat cubic in this direction. What we've done to build it is we have put our optical sensors on these strings. We've drilled these 2.5 kilometer long holes and sunk the strings while the water was still liquid and allowed it to refreeze.
Yes, is IceCube one word or two words?
We keep it as one word
Oh.
with the C capitalized, as we tend to do, but yeah. Kind of like IceCube in your IceCube trays.
Yeah.
So here, this dimension is roughly a kilometer. This dimension is roughly a kilometer. Each string has 60 of these sensors along the last kilometer of it, and the DOMs are separated by about 17 meters apart. We also have an inset region where we did more dense instrumentation for doing studies of low energy neutrinos. But I won't talk too much about those studies today. We finished construction in December of 2010, so we've been operating the full detector now for roughly 8 years. At the heart of the IceCube are 5,000 of these IceCube DOMs. They're digital optical modules. The cables from the from the deep detector are so long that we can't just send the analog signals from the photomultipliers up the wires. We have to digitize them in place. So a photomultiplier tube is a piece of technology that's been around for 50, 60 years. They're light sensing objects. They have an active surface here. They're vacuum. They're very fragile, very sensitive. But a single photon of light will hit this special material that's embedded in the inside surface of the glass and release an electron. That electron then will be accelerated inside this region. There's a high voltage there, and that one electron will then create a cascade of electrons, which will then digitize as a pulse on a wire. We digitize that pulse with a compute, basically a built-in computer. It's self-triggering, self-calibrating. These things are really, really slick piece of engineering that we designed 15 years ago. And they basically have been rock solid since we launched them into the ice, as it were. Over 10 years ago, we still have 97% of them operating deep in the ice.
Does this detect only the light coming from one direction, like from below?
So I'll show you in a minute. Yes, the active surface is below, but the ice itself is a very scattering heavy, but there are particles and dust grains inside the ice, and light never takes a direct path in this material. And it's something we have to take into account. But it does predominantly, but there also is some channeling of light from the back through the glass. So there's all kinds of optical effects that you have to take into account to properly analyze the data. It is more sensitive on the bottom though.
Will they ever run out of battery?
They're not battery operated. There is a cable going to the surface where we provide power and communications. So this thing digitizes the signal and then sends it as a data packet up the wire. And if you're ever at the University of Maryland, you can actually come by and see one. We have one hanging in our office in the Physical Sciences Complex on the second floor. This is that photocathode here. You can see the electronic boards up here and the wire that hooks into the main cable. So what does IceCube really look like at the South Pole? This is it. This is the 125 meters. This was our seasonal drill camp that we had one year. We set this up every year. This is where we make the hot water to make the drill work. And here are some of the other, radio and microwave, cosmic microwave background experiments that operate at the South Pole during the winter. And then here's our counting house here.
Did you say you drill every year?
We drilled every summer for 8 years to build the detector. And we operated it in partial configurations while we were building it. But it took eight years to build the detector. Deploying, the first year we deployed 1, the second 8, and we got better at it as we mastered our technique. In the later years, we were deploying 20 at a time.
Are you looking to detect mostly neutrinos that travel horizontally?
Nope.
Parallel to the ground, or vertically?
It can detect neutrinos in all directions with some variations, and I'll explain that a bit. But in the downward going direction, we have the cosmic rays, which are a dominant background. So to detect a downgoing neutrino, they need to be very high energy to be above that background. Upward going neutrinos we can detect without background. Another picture, these of the drill camp we used when we drilled these holes. So how do you drill a hole at the South Pole? First of all, the snow at the top is just packed snow. You can't use a hot water drill. The water would just spread out. So we use this thing called a fern drill, which is just basically a hot copper tube that you set on the snow. Then once you get down to the solid ice, you can deploy the hot water drill, and then you basically use this long drill. It's squirting out very, very hot, high pressure water to drill this 2.5 kilometer long hole. Once it is done drilling, then you lower the instrumentation down. The instrumentation gets attached to these strings by people like me, who hook this up very quickly. You're kind of racing the clock because the minute you stop drilling the hole, the ice starts refreezing. Right? We try to aim that you have a working time of roughly 36 hours before the hole gets too small that you can't deploy your instrumentation anymore. And generally, we were able to deploy it within kind of 12 hours. But we always had that safety margin that we were always worried about. But it took us maybe 30 hours to drill each hole. So it took a long time to actually melt all that ice. And it was an impressive operation. This is some of the equipment. This is the hose reel that held all that hose to drill that 2.5 kilometer long hole. And working with this stuff at the South Pole, you have to make sure you don't leave water in the hose or it freezes. You know, there's all kinds of things that working at the South Pole makes this extremely difficult.
How do you keep the hose just from getting hard itself?
It's specially engineered hose to work at these temperatures. We could not leave it outside during the winter when it got very, very cold. So it was stored in a sheltered environment where it is kept only at -20, -30.
What do you use for fuel? Fuel oil?
Jet fuel. Everything at the South Pole runs on jet fuel.
Sorry?
JPA, jet fuel.
Jet.
Oh, okay.
Yep.
Okay.
The generators, everything runs on that.
What's the diameter of this detector?
The detector, it's
Yeah, the ball, the little.
the optical modules. There are roughly 10 inches diameter, 20 inches diameter.
They're big.
Yeah, they're big photomultiplier tubes.
Is this also the place where they collect these samples that go back, say,
No, 'cause
a
it's
million
real
years to determine what was in the atmosphere?
The ice core samples.
Yes.
They have done one at the South Pole, but most of them are done somewhere else in some of the older glaciers. So this is kind of, there's actually nothing that interesting at the South Pole per se for that type of thing. There are better places to do that, and you know, some under ice lakes that they try to get to. That's other parts of the continent.
Okay.
So when you bore that hole, it's basically almost completely filled with water because there's no place for the water to leak out.
That's correct. That's correct, and it refreezes.
So other than there being a natural big chunk of ice in the South Pole, what's the advantage of having this done at the South Pole?
The ice is actually very, very good for the instrumentation, right? Once the instrumentation survives refreezing, it's a very, very stable, quiet environment. One of the things they find with the equipment that they operate at, say, the one in the Mediterranean, there is all kinds of background radiation from, you know, dissolved potassium in the water, bioluminescence, fishing trawlers coming along and catching their lines. There's all kinds of things. None of that happens here. It's a very quiet environment. In addition, we have the infrastructure from the National Science Foundation that allows us to be down here that wouldn't, you know, we wouldn't be able to do it without them. So IceCube is, you know, kind of a 1 in a billion experiment, right? So this is kind of the odds we're working on. It is one of the largest physics experiments ever built in terms of instrumented volume. I bring back this picture to kind of remind you the backgrounds we're dealing with. You know, we see these, you know, so if this happens over the South Pole, we see these muons going through our detector, giving us signals. They're muons. We see these neutrinos sometimes. They, not just the ones from overhead, but from all the cosmic ray interactions everywhere on the Earth could give us a neutrino interaction in our detector. If it interacts in our detector, just happens to interact. So we collect almost 3,000 events per second. So an event is the DOMs themselves collect data all the time, and when they see interesting data, they pass it up, and we look for periods of time where more than, say, 8 DOMs had light in them at any time. And we say, okay, that's something interesting, let's save that data and analyze it. And that's what we're doing 3,000 times per second. You know, so 100 billion events per year. And they're mostly downgoing muons from cosmic air showers that go through our detector or near our detector, give us some light, and we're able to reconstruct those paths in real time, all the time. Our background neutrinos are these atmospheric neutrinos, and we see roughly 100,000 of those interacting in our detector every year. And then our signal, what we're trying to do the astrophysics with, are these astrophysical neutrinos, and that's really just a couple hundred every year that are buried in this 100 billion. right? So this is really the number, and we're trying to identify these, and lots of effort, but we have some strong hints, right? We're looking for those very, very high energy particles to tell us something. They're higher energy neutrinos than are generally created in the atmospheric neutrinos. So we can use the energy that we observe as a strong thing. Say, look, let's take the high energy ones. Those are the ones that are interesting for the astrophysics we want to do. And hopefully at some point we're able to say astrophysical sources, they don't arrive from just any direction in the sky.
How are you able to determine the energy of the neutrino source, or the neutrino?
So you're able to reconstruct the amount of light that the lepton gives.
So it's basically how bright it is.
That's right.
Okay.
That's right. So there is some amount of they take the lepton, the electron, or the muon takes away the energy that the neutrino had, and it's brighter at higher energies.
Okay.
So these are what the events actually look like. This I think should play. Ah, good. Okay, so this is a simulation, a detailed simulation of what one of these muons going through a detector looks like. Oh, what you're seeing here are the photons being created by the muon itself and by the particles it's generating as it's passing through matter. It creates other electrons and they cascade, and you get this kind of track here, and you can see most of these photons are not taking straight paths. This is that scattering effect I was talking about in the ice. We have to take all this into account when we're reconstructing the event, and we do detailed simulations thousands of times per second, just like this one, to be able to understand how our detector works.
Do you ever detect a tau?
We have some evidence that we're starting to see the first indications of some events with a tau. I will show some examples of what a tau event will look like at very high energies, and we have not seen one of those brilliant events yet. We see some that have maybe some evidence that are consistent, and all the data we have is consistent with them being there, but they're indistinguishable to us at lower energy. And I'll have a slide on that in just a minute. But so this is kind of what these events look like when we collect them the data. These photons that interact that cross the path of one of our optical lasers, we read out the detector. To do these simulations, we use computers with graphics GPUs, graphics processing cards in them, that a lot of people have used for gaming because they can do the tracking of thousands of these photons simultaneously. So we are able to speed up the simulation of this by using these advanced GPUs to really parallelize that propagation and seeing and following each photon in the simulation. There are millions of photons in an event like this. At the end of the day, they look something like this. Here it tells you kind of where it is. We tend to have these, you'll see a few of these event views, so it's worth kind of explaining how they work. Red color indicates earlier times when the light was detected, and it goes from then through orange, yellow, green, and blue for later times. So you can kind of get an idea of the path of the particle in your detector by where it is in time and what color it is, and then the size and the density of these things tells you how much light there was. So this event, for example, was an event that happened right here in the detector. A neutrino interacted at this point and produced a lot of light at the neutrino interaction point because it happened inside our detector, and the muon then left the detector. But we can detect lots of different types of neutrinos. First of all, when you look for a muon neutrino, you're looking for a neutrino that creates these muons. These muons are very stable particles, at least on the time scale of their energy laws. They propagate through our detector and leave these nice long tracks in our detector. When these happen, the neutrino interaction could happen right here near the edge of the detector, or it could happen a kilometer away. It's very hard for us to tell. And what that leaves us is kind of a very difficult time telling what the neutrino energy was. We can say what it likely could have been, but it's very hard since we don't know where outside the detector this neutrino interacted, what its actual energy was. So there's some ambiguity there. But statistically, you can make assumptions about things and unfold what it could have been. These cascades, on the other hand, happen where neutrinos come in, interact, they produce an electron. That electron loses all its energy within a few centimeters, and just this huge ball of light is created. And you can actually measure the energy very, very well. But since there's no path that went a very long time, it's very difficult to tell the direction, what direction that neutrino is coming from. We have there is some anisotropy in the light here, but it really limits you to kind of 10 or 15 degrees area on the sky that was the potential source. And that's a huge area for astronomy. We tend to rely on these muon events because they have much better pointing, at least for us. 1 degree area on the sky is a huge area even for optical astronomy. I'm sure of it. And then there are someone who's asking about the tau events. So a very high energy tau event, what you'll see is the tau interaction, and the tau, which doesn't live very long, but if it's high enough energy, will go far enough to be separated from its creation, where you'll see this event with 2 bursts. We have not seen one of these yet, but we're waiting. We've seen, so as the energy of the neutrino goes down, these bursts come closer and closer together. So they start to look like this. So statistically, most of the taus look like this, but at high enough energy, they'll start to separate. We're just waiting for the right one to finally interact in the detector to give us this beautiful thing. These are very, very rare. The number of high energy tau neutrinos, very high energy neutrinos that you need to get to this, we see 1 per decade. So some more of these event views. This is one of these cascades. You can kind of see the size of the light ball, even though all the light originated in this very tiny area right here in the middle. The light just propagates through the ice in this, and then a nice, very high energy track. You can see that there's a lot more light being generated from this track event. You can see the size and number of hit channels goes up as it goes up in energy. This is our energy scaling up. So I'll flip through some of these quickly. I'm not going to spend a lot of time. But these are what we look at when we want to see how well an event looks. Here's an event where you can see the event, and you can see this low energy muon coming out of it. But to give you an idea of how big this actually is to something you've probably been to, this is the ellipse just outside the White House, and here is one of those events superimposed in real size on top of it. So these are 600 meters in diameter in terms of light. So that's why we need a detector of this size to be able to do this physics. The first generation of these things were only instrumenting this region. These would just be wiped out by it. You wouldn't be able to, you have to see most of this event to be able to make sense of it. So now I've got a few more slides that kind of highlight where we're at in terms of detecting we're seeing this diffuse flux of neutrinos from out there in the universe. And one of the key things we do is, looking at this energy measure, right? So we look at plots like this when we're actually doing our physics, and this is the energy of events we're seeing. So these are events that are happening inside our detector. They're contained within the detector. Not the muons, but they're ones that start within our detector. So we have a really good handle on what their energy is. And this is kind of a measure of that energy. Here is that PeV. These are these huge events we're talking about, and so far we've seen 3 of them in all the years we've been operating. But when you get down into the lower energy, you're still seeing an excess of events. Over the red are our atmospheric neutrinos. You can see they're dying away very quickly because the atmospheric neutrino interactions really can't produce neutrinos of those energies. They become very, very rare. So we're seeing these events in excess of those backgrounds. So this is what we're seeing, and this is what we've been observing for the last 4 years. We see this excess of events. We see they're astrophysical neutrinos, and it's left us, well, where are they coming from? We also see them in the muon tracks that we see going through. If we were just seeing the atmospheric neutrinos, you would expect an energy distribution that looks like this. What we're seeing, on the other hand, is the data points out here. and you can see them going out, and once you get above a certain energy, a little bit less than that PeV energy scale, you're starting to see these excessive events out here. This one event in particular out here, listed just shy of 10 PeV, it's roughly 8 or 9 PeV is our best estimate on its energy, is the highest energy neutrino that's been detected in the world. This was an event that we detected in 2013. It was a through-going muon, and it just lit us up a huge amount of energy. Its best estimate of energy is it deposited over 2 PeV of energy just in our detector alone. We say it's potentially roughly an 8 or 9 or 10 PeV neutrino that created this event. Right, so this is something that just cannot happen from something from our atmosphere. This is something coming from a distant source. And this discovery of this flux of neutrinos, was big news back in 2013, where we were on the cover of several journals, the Science World Breakthrough of the Year. But this left us with more questions than answers, because it's just the first light. You're seeing things in your detector, but you don't know where they're coming from. What are their sources? What's generating these neutrinos? Are they generated in these cosmic ray accelerator, or some exotic from some dark matter decay, or there were theories all over the map. Here, the data, certainly in 2013, was less clear. We looked at the distribution of those events, the high energy interesting ones on the sky, and we found it was pretty relative in direction. There is very likely for some of these, so some of these are a little less clear what the direction is. So these ones, the X's marked as cascades. This is the center of the direction it came from, but it's a 10 or 15 degree circle on the sky. So it's something in this circle generated that neutrino. And there's likely a source somewhere there, but we can't point to it and say that's the source. The tracks are a bit better. They're typically a 1 degree circle on the sky. Those are the green ones. And the starting tracks are a couple of degrees. They're the ones that start inside the detector and leave, and we get a good direction on them. Not as good as the through-going tracks, but again, we've done several tests on maps like this, and what we do is we scramble the times and repeat, look how often do events stack up like this. And a map like this is indistinguishable from our random samples. This is a completely, you couldn't tell the difference other than knowing this is real data or not. The other thing you can do is we have, the astronomers have given us known catalogs of objects when they're happening, things like gamma ray bursts, which are some of the brightest things observed by the Fermi Gamma Ray Telescope and have been observed for 20 or 30 years now. They're very energetic releases of energy. They're very short duration in time. They last for a few seconds, up to tens of seconds. Do we see neutrinos coming from this direction at that time? No. They're not from gamma ray bursts. Active black wave nuclei, another one. We have huge catalogs of AGNs that are out there. We're able to look for correlations, and there's no strong, when you do this catalog stacking, there's no strong indication that the neutrinos are coming from that. So lots of mysteries still remain. The data appears isotropic on our sky. How is this possible? Are they maybe they're made by transient phenomena? There's something explodes, goes off, produces a few neutrinos. We detect one. We come back and look at it later. There's nothing there of interest now. So the focus of our work in the last few years has been to work more closely with people in this doing the astronomical observations. We trigger them. We say, we saw a neutrino right now. Look right over there. Take a look. And that's a program we've started a couple of years ago. And the other way you could help resolve this is to build a larger neutrino telescope, get more events, look for multiple neutrinos coming from one spot in the sky. Increase your sensitivity. But the first one we could do without a new instrumentation, so this is what we've been doing. In April 2016, we started this program where we do this high-energy neutrino selection at the South Pole in real time on the events as they happen. We look for an interesting event. When we find one, we send it immediately north and it is broadcast to all over the astronomical world. There's a service that's run out of Goddard, the Gamma Coordinate Network, GCN. We use that to broadcast these alerts. People of interest, especially the high energy observations, tend to then point and follow these things up. Right now we're in the middle of expanding our alert selection to try to get more of these alerts out every year. Right now we've been doing roughly 4 a year. So our first one, we had really a lot of interest in follow-up. It was an interesting event. Some of these even found sources. And this really represents the biggest hurdle we have. We say, oh, there's this interesting degree on the sky, and these, some of the most sensitive telescopes in the world turn and point and look in that direction, some place they've never looked before, and they find sources. Well, is it just random coincidence that they just happen to find a supernova at that point in the sky when they point? There are a lot of supernovas out there, and this is the biggest problem we have when we're trying to do these types of observations, is kind of temper your excitement about somebody saw something. Oh, they pointed swift there and they saw an X-ray source. Well, they haven't pointed swift everywhere, and they're going to find an X-ray source when they do that. You know, they tend to find 7 or 8 when they point for us, because we are such a large area in the sky. But what we do is we send out these alerts, and then we work with our colleagues on these experiments to try to understand, you know, what is the probability that was an accidental correlation and when it's a real correlation. And we're also doing this with our friends in the gravitational wave detector when they're running. They send us their error on the sky, and we search for neutrinos. One of the things we really hope to do is, if you're familiar with LIGO, they have these huge areas on the sky where, you know, the timing between the 2 experiments tells them, okay, it had to come from this region, big region on the sky, and teams of astronomers go out and start mapping the sky. Well, if we detect a high energy neutrino, we can tell them to a much smaller area than what LIGO is capable of doing right now, where that potential gravitational wave event happened. So far it hasn't worked out, but they're going to start up again next year. So one of the more interesting ones we've had has been this multi-messenger alerts we sent out in September 22nd, 2017. It was a nice track, very well reconstructed. We broadcast it out there. A few days later, the Fermi Gamma Ray Telescope reported that this position exactly matched one of their known blazars, an active galaxy that's pointed, with the jet pointed at us, and it was in a flaring state at the time. This was very interesting, and this kind of kicked off this huge follow-up campaign by lots of people, including some of the air shrink-off telescopes that look for the very highest energy gamma rays. As they hit the Earth, they create a shower in the atmosphere, and are able to reconstruct it, and they're able to detect a very high energy neutrino, very high energy gamma rays up to about 400 GeV with the Magic Air Shrink-Off telescope at the time as well. This launched, you know, hundreds of, I think, would say 50, 60 observations across the electromagnetic spectrum. This was a result that was featured this summer in Science, and probably why people heard about this and got in contact with us. We had a big press release down at the NSF. It was a busy time, to say the least. But what was it at the center, right? So this was what we saw. So here in the region of Orion, these are our error circles from IceCube. So the outer one here is our 90% likelihood containment region. So this is where, with 90% certainty, it came from somewhere in this area. This is our 50% containment, 50% likely. These are not circles. There's a lot of, you know, we have to do a lot of dedicated computing to get these areas. It's not just a Gaussian thing. There are all kinds of effects with the ice and scattering and the layers in that thing that give you these interesting shapes and the timing of the arrival of the photons. Luckily, Magic and Fermi were able to also narrow that down quite a bit and point really to this single source here. And here is the location when you zoom into Magic and Fermi's observation of TXS there. And there was also another known AGN nearby, but it's clearly separated from this signal. This was the track itself. Here we use a different color scheme because of the request of Science for publication, but it's kind of the darker to the lighter now in terms of, you can see the arrow here. You know, it was a beautiful trek going through our detector. But part of that observational campaign was then going back through historical data over here, studying, you know, people have been monitoring the source, things like Fermi and Swift have looked at the source before. It's been searched before with some of the very high energy gamma ray detectors. It's a known source in the radio and optical bands. But here at the time of detection, you can see it's kind of this high, roughly a factor of 6 times higher flux than its normal state. And then you can see where it kicked off in terms of the optical gamma rays. And this contemporaneous observation really, I think, helped give us an idea that it really was an AGN in a flaring state, and then spent a lot of time trying to figure out how likely it is something like that would happen. Another piece of the puzzle, so this is this energy density plot that you make in astronomy, a new F-nu plot, and here you kind of see the level of gamma ray activity at that time, and here are the kind of what it would be in neutrinos from that one observation, depending on how well what time you use to normalize it. And here's the baseline, and this is the time around the observations for a half-year observation of neutrinos, which was kind of the time of flaring that this source had. You know, so it's a very good match in terms of this being a constant source. So at the time it was observed, very little was known about this blazar. It was just one of thousands Fermi knew about. Part of that observation really locked down the redshift, and it was like 4 billion light years away. It was quite far. But one of the things we spent a lot of time on is how often does something like this happen by chance? Right? Fermi sees lots and lots of sources. Now, how likely is it that this neutrino just happened to be on top of a Fermi source by accident? You know, so we used, we worked with our colleagues in the Fermi experiment. We looked at the data from all of these different extragalactic sources, looked at their light curves every month, how often, and then compared using very, complex likelihood ratio tests. How likely is it to see a neutrino, the neutrino event arriving at a time when the source was like TXS 0506 at the time we observed it? And it actually turned out to be pretty rare, roughly 4 sigma preference for a correlated emission relative to just random chance. But we have to take some trials penalties into effect there. We've sent 9 alerts and not seen anything so far. So roughly, and 41 additional events in the past that we would have sent alerts on that we've also studied with Fermi in offline studies. So at the end of the day, it's kind of this 3 sigma preference for being correlated. Now, we're not talking about discovery trough flights were done here. This is, the level we call evidence, right? We think this is interesting. We're going to continue observations. But, from this alone, 3 sigma, it's interesting. It's an interesting point, yeah.
So this is 4 billion light years away, and neutrinos do have supposedly a little bit of mass.
That's right.
Would you expect a time delay?
Not even on that distance. The mass is very small and the energy is very high. They're moving very close to the speed of light.
Okay.
But this is not all IceCube could say. We have almost 10 years of neutrino data that we can go back and look at. Previously, our searches for sources in our own data were, okay, we need something that really stands out in our data. It's very, very bright. It's brighter than anything else in the sky. But once you say, okay, I know TXS is an interesting spot. Let's take a look at that and that alone. So we went back and looked at our own neutrino data. Is it a constant source of neutrinos? Does it have some time variability in the neutrino signal from neutrinos coming from that region of the sky? And we have standard analysis we were able to just pull off the shelf and run, and we found that, during this period of time well before this burst and outburst, we see this excess of neutrinos, 3.5 sigma, 13 events over our expected background in this 6-month period. Which may not sound like a lot for a lot of things, but neutrinos, that's quite a few events. So this was also published along with that paper in Science, and this is kind of giving you an idea of what that source looks like. These neutrinos clearly look like they're coming from this spot in the sky, and they were at a single point in time in late 2014, early 2015. You can kind of see the excess building up, and then this blue line is a measure of the probability. You can kind of see 3/4 sigma here. They're capping out there before the sigma went away. We also looked to see if you just stack all the neutrinos from our 10-year sample, if you include this very bright event, yeah, it's clearly a source, 4 sigma. But we use this event to say this is an interesting spot in the sky. So it's not fair to include that in a p-value. So it's an a posteriori calculation. But if you look at all the other events, it's a weak excess, I would say, just on the whole. But it's a much stronger evidence that it's a transient source. So what is our kind of takeaway message here, right? So 2 analysis we worked to get that provide some evidence that this source is the first of these long sort sources of astrophysical neutrinos. With these results together, it says that blazars are very, especially this one itself, is a site of high energy cosmic ray acceleration. It's that first source that we've been looking for a long time, at least evidence pointing in that direction. And that blazars could be a potential source of a sizable fraction of the neutrinos we see. It may not be obvious. It may not be, so there may be some differences in what our blazar catalog, for example, will look different than Fermi's because neutrinos have a much longer lifetime. They can go much farther distances from sources. So we're going to see brighter, more distant objects than Fermi's going to see the bright nearby objects that may or may not be neutrino sources. But there's still, even after this, we have questions we're trying to resolve right now. Why is this distant, very luminous blazar the one that we saw first? Why not one of the closer blazars that are very much closer to us, but not as bright in terms of their core luminosity? What other objects out there are like that? We're working right now with people at Goddard on Fermi to help resolve this question, looking at our data, doing these detailed correlated analysis. And we're continuing our alert program, looking for the next one. And what about the highest energy cosmic rays? This neutrino was 300 TeV. It's not even, it's only 2/3 the way up that first plot I showed with that falling spectrum, right? As you get higher and higher to the rarer and rarer cosmic ray events, the neutrino flux is probably going to be there, but so this neutrino would likely have come from a 10 PeV cosmic ray, still orders of magnitude from the very highest energy ones that we see.
Could you remind us of what a blazar is?
A blazar is an active galaxy, so it's a large supermassive black hole that's accreting matter. So that's an AGN, and as part of that accretion, it spins up these jets that eject some of the material that's absorbed by the black hole up into these jets. If that jet is pointed at us, directly at the Earth, it's called a blazar. So it's a subclass of these active galaxies.
Are you saying there are closer ones that are pointing at us?
Yes. I mean, Fermi has something like 2,000 blazars in their catalog. So these are pretty common objects. But this one seems to be a distant, very large, very luminous monster. So we also continue working with people at Fermi. This is the kind of idea I was talking about there. This is, a year or two ago, LIGO had a phenomenal year where they won the Nobel Prize and then found, observed an inspiral of 2 neutron stars and correlated that with a gamma ray burst and solved a lot of the problems of nucleosynthesis all in one phenomenal observation. We looked for neutrinos from it. We found none that were correlated with the event itself. But this is something that's an ongoing work with us, where we're going to be working with them in their next more sensitive observing run that they're starting next year. And we'll hopefully be able to find neutrinos from some of these events. We're also working towards what we would do next. In the near term, we're looking at a very modest upgrade proposal. One of the things we want to do with this is, instrument a more densely packed region of our detector to really look for neutrino oscillation phenomena, to really understand the neutrinos themselves that are generated in our atmosphere. Additionally, we're going to be including lots and lots of calibration devices. One of the things that really limits our abilities in astronomy is how well we can point. If we had a much better understanding of the structure of the ice and the dust layers and all of that, we would be able to improve our angular resolution, not just for the tracks, but for the cascades, and be able to get those down to a few degrees. And that's a much smaller area on the sky than 15-degree error circle. If you can say it came from just a couple of degrees in the sky. To do that, we will include a whole suite of calibration devices in these new strings. And then longer term, we're thinking about building a much bigger IceCube, a bigger boat, as it were, to catch more neutrinos, right? So it's just how much volume you're able to instrument to be able to detect the neutrinos. So looking for a roughly a factor of 8 or 10 times larger volume, not with so many strings, but roughly doubling our number of instrumented strings. With our understanding of how the ice works, we think we can separate the strings a bit more. So that's it for the science part of the talk. I have a few slides about what it's like to live and work in Antarctica. I can go through quickly, or we can answer questions. I don't know what people would like to say.
Life in Antarctica.
Okay. So, life in Antarctica starts here. This is Christchurch, New Zealand. A very beautiful city. You go down there at the peak of their summer, and you wait here for a couple of days while you get outfitted for your polar gear, or flights are delayed. It's all a lot of, but it's a beautiful place to. And I don't know if everyone's followed the news, but in the last few years they've been just devastated by a series of earthquakes, and a lot of this stuff is not what it was when I was there. It's been a really tough road for them to recover. On your way, you stop here. This is the Antarctic Center. You get completely outfitted with everything you'll need to survive the cold in Antarctica. They don't expect you to bring anything but socks. To get there, you jump on a plane. This is an Air Force, I think that's a C-17 cargo plane. You'll notice there are two types of cargo, the non-talking cargo and the talking cargo. And they actually refer to us as talking cargo. But it's actually an amazing trip. You end up in McMurdo. This is the base on the coast. It kind of looks like a burned out mining town, and it kind of has a bit of that feel. Yeah?
When the plane lands, are they able to turn the engines off? I had a friend who was in Antarctica, and he said that basically they keep the engines running because they can't start them.
In McMurdo, it's warm enough. They land on a frozen ice runway, and they're able to shut down the jet engines. At the South Pole, they keep them running. But they're the prop planes, and they're a little hardier than the jet planes. But so you spend a day or so here waiting for your flight to South Pole. While you're there, you can take in the beauty. You can hike up the hill nearby. You can see the icebreaker and the cargo ship. At the time I was there coming in, here's the icebreaker. You can go visit Scott Hut. This is where the explorer Scott was stuck while the ship was destroyed in the Ross ice shelf. There's some cargo from back then. It's an amazing place to go see, and very few people. So they just, oh, you want to take the key and go check it out? Yeah, just don't touch anything. It's amazing. There is actually wildlife at McMurdo. These are skua. They're kind of best described as mean seagulls. And they've adapted quite well to life in Antarctica. If they have signs warning you that if you walk outside with food to cover it, because the school will see the food and dive bomb you to get you to drop your sandwich, and so they can steal it. They're quite ingenious and resourceful birds. And then a Adelie penguin all over the area. Beautiful ice structures you'll see all over this area. It's really an amazing place to spend time. But then, of course, you get on the plane and you fly one of these ski-equipped C-130s to South Pole. And then you 5 hours later, you're in the South Pole, where it's actually an interesting place. You know, you see some amazing optical phenomena that you just generally don't see: sundogs, halos around the sun because of the cold, dry atmosphere. It's amazing. There are places you go where it's quite cold. That's actually ice forming on his eyebrows and whatnot. And you generally have a lot of fun where there's things going on, movie nights, things like that, where you spend a lot of time. Ice sculpture carving contests, and you work quite a bit down there. You know, this was during some of the construction. These were there is a detectors on the surface for cosmic rays, part of IceCube called IceTop. We were finishing up the last of those when I was there. You know, you work inside buildings like this. This is kind of the late summer temperatures, minus 40 degrees C. Of course, it does get colder. Minus 78 was kind of this was a day from you know, midwinter, July. So minus 80 is pretty common that time of year. Cold, dark. You don't get out. The winter overs get out every day. They go visit the experiment in this weather. They have they set up every summer, at the end of every summer, they set up a line, a flag line, that they follow to get out to the detector in the dark. This is what the inside of that counting house looks like. These are the cables coming from inside the ice being plugged into computers to read them out. These are some of those surface detectors. They actually use DOMs just like the deep ice. And then this is...
Were these buildings constructed here, or were they basically constructed and put together there?
Everything at the South Pole, certainly at this vintage, came in the back of a C-130. So it was constructed at the South Pole. They've had some experience recently where they're doing traverses. They're driving things from McMurdo now, and they tend to drive big shipments of fuel for the winter. So they'll just put big sleds with tankers on them and drag them across the snow. But yeah, and then this is kind of a nice, during the completion year, they put flags at every IceCube station, and they really had some pretty pictures. So, but that's kind of a quick tour of what Antarctica looks like.
So, what year were you there?
Huh?
What year is this?
This was in 2011.
So, what's the typical staff number during the winter and during the summer when you're doing a lot?
So we have 2 winter overs living in residence in the station, and they stay for an entire year. We have 2. They're part of the winter over crew of about 50.
For IceCube, or
2 for IceCube of a group of 50 that cover all the experiments and man the station, including doctors, cooks.
So 4% is IceCube.
Yep.
That's a way of saying it.
Yeah, and during the
winter. Yeah.
That's in the winter, and in the summer the population goes up to roughly 200 people.
50 to 200.
Yes.
So 4 times.
And we generally have, I would say, 8 to 10 people down there during the winter months, including our winter overs, doing various tasks. That's our maintenance time. When we do upgrades, when we replace batteries in the UPS, we do all kinds of stuff like that.
Mm-hmm. What's the expected life of IceCube?
So the in-ice electronics, as I mentioned, has been very, very robust. We have roughly 96% of our original DOMs working great. With a few issues that we're able to work around, but I think, you know, of the ones that survived freezing, we lost a couple of percent during freezing, but we're losing one every couple of years due to an electrical issue or something like that. It's been very, very robust. Our lifetime is likely going to be funding limited at the end of the day, but you know, we're getting positive signs for kind of our first upgrade proposal to do these new strings. So I'm expecting we're going to be able to run for another at least 10 years, I would say, safely. But you know, it's funding dependent. Every few years we have to go back and ask for more money to operate.
said you were doing a lot of you had computers running down there. Are you
Yep.
doing most of the data processing down there, or what?
So we do the first level of data processing and classification at the South Pole. So we have, that 2,000 events, 3,000 events per second. We process all of them in real time at the South Pole it's roughly 30, a cluster of 30 computers running all the time doing this. In that one, the output of that is alerts that we send north to broadcast to the community. And other interesting events that happen in real time, we're able to identify them and send them north over fast data channels like Iridium. We're able to get a fast message out. The rest of them, we classify them and select maybe 10% that are more interesting than the rest, and we ship those north over TDRS, which is a NASA satellite that allows us to send 100 gigabytes a day. So we send that fraction up, the rest get written to tape and get shipped north eventually. But that 100 gigabytes then becomes the basis for people's analysis here in the north.
How do you physically move this 100 gigabyte, the long stuff? And what's it?
So TDRS is a store forward system. It's transmitted to the satellite, it's stored on the satellite, and then gets transmitted to White Sands, New Mexico. Okay. And then we FTP it out of White Sands. The last bit. I don't know the details of the TDRS protocols, but they handle that for us.
Do neutrinos play any significant role in the universe as we know it? Suppose there were no neutrinos at all.
Then you wouldn't exist.
Is that true?
Yes.
So that's not 100% clear. It's certainly one of the leading theories that neutrino interactions are what may have led to the matter-antimatter asymmetry that we see in the universe.
Oh, okay.
In terms of the cosmology of the universe, their mass is, from what we understand about the light neutrinos that we observe, their mass is insignificant in terms of the energy budget of the mass of the universe itself. Whether the heavier dark matter are cousins of the neutrino, it's still an open experimental question. What makes it dark matter? Whether there's some, supersymmetric neutrino-like particle. But the light neutrinos we see. But one of the things that's really driving the next generation of experiments at Fermilab and at CERN in terms of doing neutrino oscillation experiments are identifying this they call it CP violating parts of the interaction that could give rise, if they're big enough to give rise to the matter-antimatter asymmetry we see, or if it's something more exotic that happened in the hot universe.
You mentioned that neutrinos had a long lifetime. What do they decay into?
So we know of no decay that they undergo, but they can interact. So the interaction we see here can happen with some small probability in matter that they may traverse, even if it's very low density. But when you talk about the horizon back, we don't know what the actual horizon, how far back in time we can look with neutrinos. That's why that map of points of interesting neutrino events, they're very likely pointing to sources. Whether they're visible sources to us in other wavelengths is another question.
What kind of maintenance does IceCube require?
It's actually so mostly it's maintaining computer systems. We have 30 or 40 computers that are in charge of collecting the data, processing the data, and those are the predominant thing we spend a lot of time. And the custom interface cards that talk to the cables that go down the ice, or we have custom electronics that do that. But the rest of it's just regular computers, changing UPS batteries, maintaining operating systems. The winter rovers, while they're down there, also are a member of the South Pole, population. They're firefighters down there. They're cooks. They work in the dish pit. They do all that stuff that just living as part of that community.
Are most things run on Unix?
Yeah.
Okay, so everything's Unix, no Windows.
Well, let's thank our speaker again and feel free to.